Basically, after we made a release, but I guess it has interest.
Okay, we'll start with Bart's portion of his start.
Thank you very much. Yes, we'll continue the journey into Kadison Duality. I'll summarize briefly what I talked about yesterday. So there was this overview diagram with the different categories I've been talking about. Especially, I followed this left about vector space, especially with the norm. And the main result that I discussed yesterday is that you have this isomorphism for a normed vector space. The space itself is isomorphic to the continuous dual of its norm dual. So this prime is the set of continuous functions, weakly continuous functions on this V sharp. And V sharp is the set of V sharp is the set of linear and bounded functions bounded in this norm, and the weak star topology that I'm using here is the least one that makes all these point evaluation functions going to be continuous. So this is this isomorphism is what I will use tomorrow at the end to prove Kadison Duality. What I want to do today is go up this leg on the other side and talk a bit more about order unit spaces, which are probably a bit less familiar. And the work I will be talking about today is a bit less classical than what I discussed yesterday, which was basic vector space theory. So let's start with a vector space with an order. It's a space with a partial order satisfying some elementary requirements, basically requiring that the order interacts well with the vector space structure. So if two elements are ordered, you can add a third one on both sides and the order remains intact. And similarly, you can multiply with a scalar, but the scalar must be a positive real number to keep the order. And we'll use the notation O-vect for the subcategory of these vector spaces with linear maps which are monotone, which preserve the order. And in this context, probably good to, to mention that the space, if you're familiar with this notion, is an order vector space which additionally has a join, and I'll probably briefly talk about spaces also tomorrow.
Do you demand it to be lattice ordered or not?
Well, there is some some divergence in terminology here in this area. What is a lattice? Most people, at least in the background I come from order theory, call a lattice where you have also a top element. So not only a binary join but finite joins. And here in this tradition, people call a lattice, speak of a lattice if you have a binary join already. And so there's some friction of the terminology. But certainly you don't want to have a top element because in the r to the power n, for instance, you don't have a top, or simply an r. And then there's another slightly difference in topology in order theory and domain theory. People tend to speak about monotone functions. In this tradition in functional analysis, people talk about positive functions, but basically this means the same because we can subtract elements. It's clear that a function which is monotone is also positive, and positivity also applies monotone, because if v is less than v prime, this means that v prime minus v is bigger than 0, so f v prime minus f v. So f v prime is bigger than f v. And these properties that I'm using here follow from the properties of the user. So positive and monotone means the same, and I'll use them exchangeably. Is that word? Exchangeably.
Interchangeable.
Interchange. What's now a unit order space? Well, I need another definition. A strong unit in such a vector space is a particular positive element, typically written 1 in this context, such that for an arbitrary element it can be squeezed in the interval minus n to plus n by taking a suitable natural number n. So everything can be squeezed in by making the interval large enough. And such a unit is called Archimedean if this condition holds. So if I can prove that for each positive real number v is below r times 1, then v must be below 0. Right? So it's a way to push an element below 0 by proving that it can become arbitrarily small, or it's bound to be arbitrarily small. And an order unit space is an order vector space over the real numbers, sorry, restricted over the real numbers, which has such an Archimedean unit. And I'll use the subcategory order unit spaces with maps which are positive and uniform. I'm not fully aware of the meaning of this PU, so I should be informed about that. Maybe over a beer.
He's the expert.
Sorry?
Prakash is the expert.
Maybe I can change that to UP.
Yeah, that would be much better.
That would be much better. But unitive positive, although it doesn't sound so, so nice. Sorry? Yeah.
Up.
Yeah.
Unital positive maps.
Unital positive. And a unital completely positive map? Okay. I'd like to hear over a beer what it means. Okay. Anyway, these slides were written before I knew about this. No one informed me, although I do have some English-speaking people in my environment, no one told me. How order unit spaces may arise in different ways from the main categories I was interested in the beginning. And I will spend some time discussing this diagram. So order unit spaces arise from sets, from convex sets here, from compact Hausdorff spaces, and from convex compact Hausdorff spaces. There are all ways to construct these order unit spaces. And what's interesting, we'll see that all these functors have right adjoints. these right joints are given basically by taking states. You know, so it's a very nice uniform situation. Now, I've been talking about convex sets already a few times, but I haven't said precisely what they are. And they're simply sets in which finite convex sums exist of finitely many elements x, y from the set itself, and finitely many probabilities Ri which add up to 1, like this. Often people require that there's an R module structure around, but I don't in this situation, just the existence of these formal sums. If you're more categorically oriented, these convex sets can be described as Heisenberg-Moore algebras of the distribution monad. So there's a nice categorical description of it. There's a historical description going back to Stone, where he uses a sum like this, x plus r, where r is a real number between 0 and 1, which can be understood as r times x plus 1 minus r minus y, in this sense. And you can prove formally that this description corresponds to the Heisenberg-Moore algebra description. And several people have already done that, including Schwierz and Klaus Kahn, worked on this. But I'll use simply this more concrete description. Affine functions are the functions that preserve such convex sums. They're simply the Heisenberg-Moore homomorphisms, if you like. Let's look at this functor first. L infinity, going from sets to order unit spaces. What does it do? It takes a set and you take the bounded maps to the real numbers. And bounded means that there is simply a bound B such that the absolute value remains below B for each x. The vector space operations on this set are inherited pointwise from the real numbers. The order is also the pointwise order, so two functions are ordered if and only if each element you have is. There's a unit, and the unit is simply the function that's constantly 1, and it's strong precisely because maps are bounded. Because we have these conditions that maps are bounded below a real number b, so I can take a natural number above it, and basically I then get that phi of x is below n, like this. This is what I can write down, and in function terminology I can write it down like this, where 1 is constantly one function, so this whole stand element applies. So it's crucial that functions are bounded in order to get order unit space. The Archimedean properties follows directly from the property for the real numbers. This is a functor. It also can be applied to functions, but in a contravariant way. And because this is simply done by pre-composition, all the structure is preserved. The second function, A infinity, A for affine, goes from convex sets to order unit spaces. And the definition is basically the same. You take bounded functions, but now the affine functions to the reals. And again, the order unit structure is precisely like for L infinity, and you have pointwise operations. And the only thing you need to check here is that these affine maps are closed under the vector operations. For a compact Hausdorff space, this is the classical definition that has been used already a number of times here in this room. You take the maps to the reals which are continuous, and an elementary result in topology says that the image of this map is then also compact in the real numbers and thus bounded, closed and bounded. And, so I can drop the condition of boundedness. My next one, I'll write AC for the affine continuous functions from x to the reals, and this all works in the same way. As a side remark, the L infinity and C construction, they yield C star algebras, but the other two constructions, they don't yield C-star algebra. Of course, you have to extend it to the complex numbers if you want to get the complex C-star algebras. So we're doing something else here with the by using the affine functions and what's known for C-star algebras. Because the key property is that the affine maps are not preserved in the multiplication. Now this is a crucial slide now. What is a state in an order unit space V? It's an up map going from this space V to the real numbers. So it's monotone and preserves the unit. And the real numbers, this is a theme I'll explore later this weekend also. The real numbers is not hard to see. They are initial in the category of order unit spaces because 1 must be sent to 1 and this extends linearly. And order unit spaces is a category that's conveniently understood in opposite form. So the real numbers are final in the opposite category, so I can write it as 1 there, and then a state is simply a point in the opposite category. It goes from 1 to the space V itself. And a nice example is the states on the real numbers, the power n are probability distributions on n. So states now what is the state Rn? Is a map like this, and let me write I for the unit vector with a 1 on the I position and zeros everywhere, and I define R sub y is omega in this basis vector I, which is in R. Now this I is a positive vector. Omega is a positive functional, so this will be a positive number. Moreover, if I add these i's, that is the sum of the omega of all these base vectors. Now omega is linear, it's omega of the sum of all these base vectors. This is omega of 1. Which is 1 because omega is unital. So you see that distributions, distributions over n arise naturally from these states like this. In the other direction, it's very easy now to see that if I have n numbers adding up to 1 and positive numbers, that gives me a state like this by linearity. So states indeed, they give you they describe a certain situation in probabilistic terms, at least in this situation. To do a bit of logic in this situation, you need effects. Effect is a positive element below the identity. I'll write this unit interval sub v, the set of effects. And effects, they correspond to maps from R squared to V. I think I showed this yesterday, how to do this. And if you do this in the opposite category, R is 1, the R squared is the product of 1, in the opposite category becomes the sum. So these effects can be described as let's say general predicates going to 1 plus 1. By the way, the same can be done in C-star algebras in the opposite if you use these positive unit maps. And it's not very hard to see then that the effects in R to the n is the cube 0, 1 to the n. Because you need to have in each coordinate that things are below 1. So this description here is fairly simple. You can talk about validity in this context. You call this the Born rule. You can speak about the validity of an effect V in a state here. Omega gives a certain probability, and this probability is simply a obtained, defined in this way simply by function application. And if you want to describe it a bit more abstractly in the opposite category that should be done, it's simply composition of a state and the effect, which gives a map from 1 to 1 plus 1. And these correspond to probabilities in a more abstract setting. Again, this is a theme I will explore a bit more abstractly if we can. Any questions about that? Good. In my introduction, I briefly mentioned effect modules and effect algebras. I have not given the definition, but I would like to point out that there is a close connection between all the unit spaces and these effect modules, simply by taking the effects in such an order unit space. And but you need to have the Archimedean property also in the world of effect modules. This works out nicely. In the other direction, going from an effect module to an order unit space, you just have to complete the partial operation that you have in an effect module to a total operation together with the module structure. This can all be done in a nice form. This even extends to the complete case. There is an equivalence between complete Banach order unit spaces and complete effect modules. But I will not pursue this here. What is worthwhile pointing out that is the set of maps between two order unit spaces that carries some algebraic structures. Namely, it has the structure of a convex set. So if I have a finite collection of maps Fi from V to W and some real numbers that add up to 1, I can form this function simply pointwise. Let's call it F. It's not hard to see that this function is positive. Again, the challenge is to prove that it's unital, but again, this is not very difficult. But here you crucially use that these Ri add up to 1. So the definition of F is simply this, element-wise. Now, Fi is unital, so this becomes a 1. So these can be added separately, which is 1 times the 1 of the unit, order unit space, and you get 1 as an outcome. So these sets have a convex structure. Because pre and post composition preserve these convex sums, I'm inclined to say that it's enriched over complex sets, but frankly I don't know if tensors exist of these order unit spaces. As far as I know, it's not. Anyway, we do get a functor like this from the opposite of order unit spaces to the convex sets, because states, remember, are just the home sets into the unit numbers. So it's a special case of this more general lemma here. At this stage, I can claim the following results: that the two functions L infinity and A infinity that I described earlier, they both have states as right adjoints. So here I use that states really go to convex sets, and here, well, convex sets are also sets, so I implicitly use another forgetful functor. These adjunctions are very, very simple, the typical kind of adjunctions you get in such a duality setting, namely you simply swap arguments. Let's look at the first one here. You need to prove a bijective correspondence between maps F and G like this. They are on the same side. For an adjunction, this must be on the other side. But notice here I have not written the op here on the category of all the unit spaces. And this is just swapping arguments, because this is these are maps from X to R. So here I can put in the X, and these are also maps from V to R. The only thing that has to be checked is that they satisfy the properties. This is rather trivial. these adjunctions do allow you to prove some elementary things. One property is to show how the A infinity and L infinity are related, namely via distribution moment. This is a categorical result. If you don't know this kind of categorical way of reasoning, if you haven't seen this, then I'm unable to explain this in a minute, but the main story continues in a minute. So the reason goes like as follows. We've seen this adjunction and we've seen the outer adjunction. Because then this adjunction between sets and convex sets. Now two adjunctions compose, like this one. So in the end I have two adjunctions between sets and all the unit spaces opposite. So they must be isomorphic because they have the same functor here. So the left adjoins, these two must be isomorphic. It's not a spectacular result, but it's a reasonably nice way of reasoning about these structures. I'll show you some other examples in a minute. Okay, the next thing we need to observe is that each order unit space automatically carries a norm. The order unit norm, I've written it here explicitly, and you take the, remember that arbitrary vectors can be squeezed in between natural numbers. You do this squeezing in now with real numbers. In this way, you know that the set over which you take the meet here is norm-empty, and the Archimedean properties then take care of the fact that it's nicely behaved as a norm. What else? The induced norm, for instance, in this space L infinity of x that we saw earlier as an example of order unit space, that's the so-called supremum or uniform norm. You simply take the supremum over all the absolute values that this function takes, and this supremum exists because remember these kind of maps are bounded. Again, you take the supremum over a set which has an upper bound. Now the same result holds for these other constructions of order unit spaces, A infinity with continuous functions on x and the affine continuous functions on x. And actually it's the case that all these spaces are there complete in their norm. Useful result now is that each map in this category of order unit spaces, remember that for morphisms we have this operator norm, and this operator norm is for all these maps precisely 1. And I will use that a number of times later on in reasoning. And the norm is precisely 1 because these maps are unitary, so F1 goes to 1. And a bit formal way of saying this, in particular, we have that the states, which are maps from V to the real numbers, are bounded, and their bound is less than 1. You can even say it's actually. But this is a useful result because remember from last time that this set, this ball of linear functionals was compact. It was compact in the weak star topology. And we have a subset here of a compact space, so the states also in this case will be compact. If I remember well, that's the next slide indeed. The states on this space of linear functionals, this bounded linear function, is a nice compact set in the weak star topology, which just to remind you is given in this way. A proposition that says indeed this is a compact Hausdorff, and an alternative basis for the topology you have here can be described in this way, this box notation that you sometimes find in probabilistic logics. It can be used here in this setting as well. And also each map induces a function by p composition in the other direction. Now, what's the proof? As I already said, states are a subset of a space of which we already know that it's compact, and then the rest is easy compaction house. With this in mind, we can have two more adjunctions where states are right adjoints to functions that I described earlier. We remember C is taking continuous functions into the reals in this case, states as right adjoints. These take the affine continuous functions into the reals. And again we have states as right adjoints. Now, these adjunctions allow me to say a few more things again by purely categorical reasoning. The first one says that taking continuous functions after U is L infinity, and what is U? U is here the ultrafilter monad, so sometimes written beta. And you can see this in this diagram. So sets and compact Hausdorff space, the forgetful functor has ultrafilters as left adjoint, and from compact Hausdorff spaces you can go to order unit space by taking continuous function. So this one must be then equal to this compensation, or naturally isomorphic. So again, that's a reasonably smooth way of relating some very basic functors in this area. The same reasoning can be used here on this side. I have not explained this situation. This is the expectation monad that I described in some earlier work with these students of mine. If you don't know, it doesn't matter too much, but if you take the expectation monad, then a fine continuous function. Again, this is simply taking the bounded functions. Good. So the situation can be summarized like this. Then I have a category of order unit space in opposite form in the middle, adjunctions with sets, with convex sets, with compact Hausdorff space, convex compact Hausdorff spaces. And this nicely sums up what I've done so far, but a bit more can be obtained like this. Because of these adjunctions, you get monads on all these endpoints. Some of these monads are also known from previous situations, especially this monad here is this expectation monad that I talked about earlier. This is the Radon monad that Robert and I worked on in another paper. This monad is, as far as I know, not used yet in program semantics. It makes sense to do program semantics also in a category of convex sets, especially probabilistic semantics. But what this monad is, then I don't really know. It's a bit, well, I know what it is. It's obtained like this, but I haven't seen it being used in the literature. This adjunction is what I will continue with, and I hope you see this is already fairly close to Kadison duality that I'm really after, between all the unit spaces and convex Hausdorff spaces. Just to say a few words about this monad, the Radon monad. It's a monad on the category of compact Hausdorff spaces, and the main result I had with Robert follows on to the Gelfand duality that you described this morning. So Gelfand duality gives the equivalence between compact Hausdorff spaces and C-star algebras, commutative C-star algebra with star homomorphisms. If you change your homomorphism, you go to the positive unital ones. These positive unital ones are, I would claim, more useful in computational situations. Then you can describe this category as a Kleisli category of a monad, which I think is a very nice result, because it shows that at least this world of probabilistic computation can also be described in terms of monads, which is an approach that has been developed quite extensively in the programming semantics community and gives a connection with the functional analysis community. A big challenge, by the way, is to get a similar result for C-star algebras without the commutativity. can report some progress on this. So another PhD student of me and Emming has worked on this and claims to have also a monad-like description of this, but the thing is we don't know what the monad is. I mean, we can see that it exists on the basis of very general arguments and joint functor theory, but we don't have a handle on it, so it doesn't help us. But it's ongoing work to get a better handle on this situation, and hopefully also describe the proper quantum case in terms of a monad and a class literature. Good. So, as I said, I'll continue with this towards the goal. Now, the easy half of Kadison duality is the injunction from this diagram. This restricts to an injunction between convex Hausdorff space with this separation property, where points can be separated. And moreover, the unit of this injunction, which has this form, it goes from a space X to the states on the affine continuous functions on X, and it's given by evaluation like this. This one is an isomorphism. And what I will do in the remainder of this talk, I don't think I need a full hour, but I'll go through the proof, because it contains a nice argument which can be explained in one slide. So it's easy to see that this evaluation is continuous and affine, and it's injected precisely by this separation condition here. Because if evaluation of x on phi, which is phi of x is phi of y, is evaluation of y on phi for all phi, I need to prove that x is y, but this is precisely this formulation of this separation condition. So the separation condition actually forces this unit to be injected. And for surjectivity, we use that X is already a compact space, so it suffices to show that the image is dense, and this gives me surjectivity. Good. Now, in order to prove this, I need an auxiliary result, and this is a result which has actually a nice proof, which makes use of the convexity that you have in this situation in an essential way. And the lemma says that if I have a function which is affine continuous from x to the real numbers, and if I have a state in this, a state on this order unit space, then there is an element such that omega phi is phi of x. It's a sort of barycentric description of the situation here. You have a question? Okay, how does proof work? Let's go step by step. The image of phi in the real numbers is compact and is bounded and closed, but it's also convex. So X is a convex space, so the image is also convex. Now think for yourself, what is a bounded, closed subset which is also convex? It's fairly clear then that this cannot consist of separated, of disconnected intervals. It must be really one interval, and because intermediate points must also be in there because of convexity. So this image is of this form. Phi of x is a closed interval from S1 to S2 in the real numbers. I'm going to massage this interval a little bit, and I'll take the middle, m, and I'll take the radius, and then I'll write this interval as the set of t's, such that the distance of to the middle is less than the radius. It's just, I'm massaging it a bit so that the taste is full. Okay, now our next step is I take this function. So I start with phi, but I massage this one also a bit. I change phi into phi minus m times the identity 1, and the identity is a function that's always 1, I remember. And m is this middle of this interval, and I take phi minus m times this identity. I'm going to look at the norm of this function. And I claim it has R as upper bound. So the norm of this function, the norm in this space is the uniform norm, the supremum norm, which I compute here. The supremum over all elements applied to this function. But this part is simply constant. So I take the supremum over phi x minus m. And because phi x is in this interval, the distance between phi x and m is at most r. Because the interval is r1 or 2r, right? So this has r as upper bound. What I do next, I have also a state, and for the state I know that it has operator norm 1, and I'm applying omega phi minus 1, and I look at the distance. Well, omega is a linear function, which is unital, so this is omega of phi minus m times 1. This is pure linearity and the fact that omega of 1 is 1. Now, omega of this is less than the norm times this, but the norm of omega is 1, so it's simply less than this, which we've seen in this argument is less than r. So the distance of omega phi and m is less than r, but that means that omega phi must be in this interval. Right? Thus there must be an element x such that omega phi is x. Right? So it's a highly non-constructive proof using these norms. But it works nicely. So this is one of the proofs that was hidden somewhere in the literature, and I was happy to find at some stage that I could plug this in to complete the proof. I'm still not done, because what I need to prove is that this image of the evaluation map here is dense. But now this can be finished very quickly. How do you do this? You take an open subset here and a normal empty open subset here, and you have to prove that the intersection with this evaluation x is normal. So I take a non-empty open subset here, and as I showed before, it can be described in this box form as the set of omega, the set of states, such that omega phi is bigger than s. For some phi here and some as actual rational number. We have to show that the intersection of this with the image here is non-empty. We know that this open set is non-empty, so there is a state, an omega, for which omega of phi is bigger than s. Now I have an omega and a phi, and my previous lemma says then that there must be an element x, such a Barley center, such that omega phi is phi of x, which is the evaluation of x and phi. But because omega phi is bigger than s, that means that the evaluation of x is in this open set, hence the intersection of these two is non-empty. Good. That finishes my work for today. I'm doing the rest tomorrow. I know it takes a lot of effort to go through these proofs, so I don't want to do more than this today. Any questions?
Okay. First. Well, your comment about the non-commutative case, that you had there was
A monad? Yeah.
yeah, so what, can you tell me, I lost track of exactly what it is you were referring to there.
All right. Essentially, let me try and describe the commutative case first, for commutative C-star algebra. So commutative C-star algebra, I'll use this notation, MIU for star homomorphisms. Multiplicative, involutive, and unit to numbers. So we know this is this is equivalent to C is I'll drop you off so for a moment. The commutative C star with the up maps, unital and positive, they are in here. Star homomorphisms are automatically positive and unital, and this one has an adjoint. And via this adjoint, you can prove that, well, this adjoint gives a monad here, that the Kleisli category is then isomorphic to this one. And here you get the standard adjunction. But the crucial thing is proving that you have an adjoint here. Now, what this student has been doing is basically drop the commutativity, look at this inclusion, and try to find an adjoint to this. The answer to this is looking at reservations. I have to be careful about this inclusion preserves limits. Because there's this op involved, and if I remember well, if I describe it like this, there is a right adjoint to this one. Oh no, sorry, then it should preserve. Well, forgive me if I forget about these digressions, but at least appropriate structure is preserved, and then you have to find the solution set condition. And that's basically what you do.
Okay, so I guess the one hint I'd offer is that there is a non-commutative version of the Gelfand
Yeah?
duality. That's the Downs-Hoffman theorem.
Yeah?
And I'm thinking that maybe if you went on this other side over here,
Ah,
but that's a bundles construction as opposed to a sheaf.
Okay.
You can view the commutative version as a sheaf.
Yeah.
Of the Gelfand. The Gelfand duality of Prakash, you can think of it as a sheaf construction. The non-commutative is a bundle construction.
Yeah, yeah.
And then you end up with something over the bundle on the left part of your diagram.
Yeah.
So,
I appreciate your comment. The work is so recent. I haven't looked into
I'm
the
just
details.
chasing down what it is you.
And I'll certainly pass on your suggestion to look at Downs-Hoffman. Robert, you were raising your hand?
We were able to calculate a couple of examples.
Oh,
We
yeah.
were able to calculate the complex numbers, the C squared, and we were able to prove that the C cubed is non-commutative, so it doesn't preserve commutativity.
Yeah. So the current stage is, know it exists and trying to find out what it does in some known cases and see if we can find a bit more structure. Yeah. But certainly it's a non-trivial function. Yeah. So in the end you can ask whether it's very helpful or not, but it's certainly intriguing. Yeah.
What is this right adjoint in the commutative case?
I think so you go like this. So what you can do is you take the states and then you take a continuous functions on the state. But here you have to be a bit careful which states you take, and I think you take the UP states then, because you can also take the mu states, which are basically the structures you use, the mu states, which are the ideals, maximal ideals. It gives you a spectrum. So I think it's this one. Right, Robert? Are you following? What is the right adjoint?
That's depending on the states or something.
Yeah, or something. Thank you very much. Yeah. This is yeah.
Another one. These adjunctions with the little L infinity, does that generalize the capital L of the measure space?
Yeah, interesting. I haven't worked it out. That could well be. Yeah, it would be nice. I'm pretty sure it's a good question anyway. So I've had 4 maps going into all the unit spaces. But there is definitely a 5th one, namely starting from measure spaces, doing the construction. Yeah.
I think I'm missing an obvious point, or I'm just being dense, but you showed that this one of those sets in your lemma was dense by showing that it intersects any sub-basic open, right?
Yeah.
Don't you have to show that it intersects any basic open?
Yeah. Maybe I was cutting some corners.
Just leave it like that.
Yeah, no, you're right. Sorry. Can't remember whether these sets are.
Maybe they're basic.
Yeah, maybe they're basic. Maybe that's. I did look into it, but I forgot that there was a little step. Yeah. Thanks. Yeah.
I have a question which more in social nature. Have you had any interaction with like these old quantum logicians like Fulmanov and all these people who are doing effect algebra, and how do they buy this into this?
There's interaction in the sense that I've read their papers. I've met them a few times at conferences, but I didn't have extensive contact with them. Anyway, my impression is that they don't think in categorical terms. So I'm afraid they don't see, they don't follow. I've had some contact, especially with Fulmanov and Diverensky. Yeah. So he does know some categorical. I appreciate very much the work of Stan Gutter and Paulus, you pronounce it? Fullis. I never tried to get a good contact with them, but I think they're pretty old. I don't know if No. So at some stage I tried to look up their webpage and I remember I couldn't find them. So yeah.
Stan Gutter is around.
Stan Gutter is still quite active, I think.
Yeah.
So he's formalizing Sorkin's quantum measure theory.
Okay. Yeah. So maybe I should have made more effort here. But somehow I'm also suspecting that they must have been referees at some stage. In submitting it. I guess so.
Any more questions? No? Okay, we got 5 minutes, but we can just slowly.